and
Okay.
maybe I will read it. So then the title is Wald Zoupas charges in asymptotically de Sitter spacetime. The speaker is Maciej Kolanowski from Warsaw. Okay.
Okay.
Please.
Thank you for the introduction, and let me thank the organizers for an opportunity to speak here. So I want to say a little how to define quote quote conserved charges in spacetimes which are asymptotically de Sitter. So basically today I'm mainly interested in solutions to Einstein equations with positive cosmological constant. So the first question that comes to mind is why should we care about it? The main reason is that physical cosmological constant is positive, at least according to our observations of the universe. So this is exactly so we will try to define charges in our universe, say. It may be kind of surprised that this is still a work in progress in 21st century, when there was a lot of developments in asymptotically flat and asymptotically anti-de Sitter case. There are a few reasons why positive cosmological constant is harder. First of all, because null infinity is space-like. So as a result, we don't have any time translation, generator of time translation. So all charges could be either positive or negative as a result. We don't have the only universal structure on Scry is this of a differential manifold. So there is no universal metric, no universal class of conformal metric, as it is the case in asymptotically anti-de Sitter spacetimes. We only have smooth manifold. And as a result, asymptotic symmetries in general are all diffeomorphisms of null infinity. So there is no way to distinguish generators. And well, since I want to say something about physics, a natural question is whether we can measure whether those problems could be somehow signalized in gravitational wave astronomy, and certain phenomenological models suggest that it should be possible in the next generation of detectors to measure some lambda corrections. So this is why we actually need this framework. So I'm going to first sketch Wald Zoupas' approach to defining charges in asymptotically flat spacetimes, then extend it to asymptotically de Sitter spacetimes, also proving uniqueness of our constructions, and comment on some examples and open problems. The general idea is very simple. We foliate our spacetimes by some hypersurfaces sigma, which asymptotically looks like null cones, and they intersect at some point Scry after conformal after some conformal transformation. And then we want to assign some form of Hamiltonian to each of those sigma surfaces, and then we would have conservation law, which simply states that energy of the first of sigma 1 is the same as energy of sigma 2 plus energy that was radiated away. So what we actually could measure is this F, which is a flux of radiated energy. This picture looks very similar when lambda is positive, with the only difference that Scry now is space-like surface instead of null. So now to this Wald Zoupas algorithm. From the definition of Hamiltonian in symplectic geometry, we have that it should be given by symplectic form in the following way, However, right-hand side is more often than not is not exact variation. So as a result, this Hamiltonian does not exist. This is why we use this crossed delta to signalize it. Indeed, we can take quote, quote, the second variation and check that in general it is not it does not vanish. So it means that there is no such Hamiltonian. The idea is to change this definition by adding something, so it would be a true variation. Now, in practice, as we have seen here, this variation of Hamiltonian is described only by boundary term. So we're interested in symplectic in the limit of symplectic form at scry. So we take the limit and then pull back to scry. If we can find some presymplectic potential for the limit, then quote unquote correct Hamiltonian would be given by the following variational equation, and then this second variation truly vanishes. And there is then very simple formula for flux of this quantity. It is given by this presymplectic potential. Of course, we have an ambiguity that presymplectic potential is defined up to adding to it some full variation. So we need to somehow get rid of this ambiguity to obtain some meaningful results. Otherwise, we could obtain almost anything as our Hamiltonian. Wald and Zoupas, to prove uniqueness of the added several constraints that this presymplectic potential is supposed to build only out of dynamical fields and available universal background structure. So, for example, in asymptotically flat spacetime, this is metric in some Bondi frame. It should vanish whenever evaluated at a stationary background. So here phi, this dynamical field is stationary, and the delta phi is arbitrary variation, and then it should vanish. It should depend analytically upon dynamical fields, assuming that Lagrangian also depends analytically in them, and it shouldn't depend upon any arbitrary choices. The main arbitrary choice one could make is conformal factor. And then they were able to prove that there is exactly one such theta in asymptotically flat space. Okay, now we will work a little bit with positive cosmological constant. So around scry, we can introduce so-called Pfefferman-Graham gauge, which looks like this. And this metric on rho equal constant slices has an analytical expansion in rho. The first, G0 is free data for Einstein equations. Then G1 and G2 are given by Einstein equations. In fact, if I remember correctly, G1 is simply 0. And then G3 is again freely prescribed, only up to certain constraints that it's supposed to be traceless and divergenceless with respect to this G0 metric on this slice. For convenience, let us rescale it so to make some connection with works on holography, because in ADS CFT, this TAB or in any holographic theory, this TAB tensor has interpretation of being a stress energy tensor of holographic theory, which lives on the boundary of our spacetime. Those G0 and T are defined up to conformal transformations because which simply corresponds to different choices of rho equal constant slices. From the work of Friedrich, it follows that that conformal class of G0 and T uniquely defines solutions, at least in some neighborhood in phase space of the sitters. In the Pfefferman-Graham gauge, it simply means that we have some recurrence equations for all higher terms in our expansions, which can be solved without any additional integration constants. Now, we need to find limit of the symplectic current to Scry, and it is very easily, this limit is has very simple form using this T and G0. And in fact, this limit is equal to the symplectic current in Scry, which simply means that symplectic current in the bulk, which means that we don't lose any degrees of freedom, and Scry is a Cauchy surface here, as again follows from the previous slide. So one immediately can see that we can take the following theta as our guess. Then we add it to the definition of the Hamiltonian, and this Hamiltonian actually truly exists, and it looks very similar to the, say, Komar mass, to the Komar charge. It was actually proposed over a decade ago, but without a proof of uniqueness of this Hamiltonian, which will now fill in. So we had those four conditions in asymptotically flat case to restrict theta, but we cannot assume the second one because there are no stationary solutions near Scry when lambda is positive. So we can, but apparently if we cross it out.
Can I ask a quick question? So in the previous slide where you defined the charge.
Yeah.
So the C are basically symmetry generators associated with G0, the boundary metric. Is that what's going on?
Yes. So basically those Xi's are could be any vector field which is tangent to Scry.
Yeah. Okay. Thank you.
Thank you. I should said it. Okay, so we simply resigned from
There's
this.
also a question from Philip Ficek.
Yeah, sure.
Philip? Okay, no question. Sorry. Philip?
So we don't need to assume the stationarity, and even then uniqueness follows, because apparently this conformal invariance is much stricter constraint when lambda is positive, so on space like null infinity. But as it was actually told, we have too many of those Hamiltonians because they're associated to any diffeomorph, any vector field on null infinity. So there is we don't have any idea actually how to then define good energy. But what we can do is calculate it in linearized theory, say around de Sitter. Then flux has this particular form, and it is actually the same as it was derived last year for a linearized theory around de Sitter. So there is at least some connection, and moreover, in those papers, it was checked that this expression has the correct limit as lambda goes to 0. It means that this flux of energy simply goes to Trautmann-Bondi mass loss law. One could, in the same manner, we could treat perturbations around the Schwarzschild-De Sitter black holes, because there we also have distinguished rotation generators and also time translation. This time translation is defined only up to scale among Killing vectors, so this energy is also defined only up to scale. One observation is then that if we consider gravitational waves, which only has magnetic part but no electric part of Weyl tensor, then they have no zero energy density, but this density integrates to zero for the whole sky. Now, we could also try the same with Kerr-de Sitter. Again, we have some unique angular momentum given by d upon d phi, but there is some problem with energy. Because there is no, we don't, normally one chooses a generator of energy as this Killing vector, which goes to d upon dt at infinity. I mean, normally it means in asymptotically flat spacetimes, but here at infinity it is not so well defined. So it seems that a better choice would be to choose this Killing vector in such a way that it is perpendicular to the angular momentum generator, because, well, this is conformally invariant condition, but on the other hand, we don't see for now any physical reason to choose this particular generator. And there is still this question how to extend this or some other choice away from the Kerr-de Sitter, so beyond perturbation theory to the full theory. So we have derived charges and fluxes, shown that they are unique under very mild and natural conditions. Their expansion and around, say, de Sitter spacetimes is, as one would agrees with linearized theory, and we have the proper lambda goes to zero limit again in this expansion. But we still don't know how to define energy and other charges in the full non-perturbative general relativity. Okay, thank you for your attention.
Okay, thank you. So, are there any questions?
So yes, I would have one. Is this so your charges are defined for any vector fields, right? They don't have to be any Killing or anything like that, right?
Yes.
Is this
yes.
correct? Okay. Now, there's an issue which we discussed recently, whether when you take this symplectic form and try to push it to scry, whether it converges. So have you been able to clarify this? Is this really true that you get a this
so
limit that you wrote?
So for now, this is argument from the literature that people claims to be so, but I haven't checked it by hand yet.
Because I have doubts about equation 12, right? But of course, maybe you can just discard some diverging terms and still get that. So there's nothing wrong using this.
Okay.
But
may I comment 12? So first of all, I have proved many years ago, but in the context of ADS, that the natural ADM data, which appears on a finite surface, when it approaches scry, it behaves like that. So the idea is that there is some divergent term, but this is full variation. So this symplectic current has a precise limit, and this proof does not depend on the signature. So I can say that I have proved this formula 12 in my paper, but I didn't use it for de Sitter. So, but the proof is the same.
Okay, I would love yes. So I would love to see this actually. So if you could
try my
can you send me a reference to Jacek?
Yeah, this Acta Physica Polonica, you know, there's only one paper about it. So
Jacek, there are some questions from the audience, Laura and Igor. So maybe Laura?
Yes, thank you. Yeah, actually, my question is related to, can you hear me?
Yes.
Yeah. My question is related to what you were discussing, actually, about the uniqueness of this presymplectic potential, even for asymptotically flat spacetime. Like, I mean, now we know that, you know, I don't know whether you had specific boundary conditions in mind, because now we have understood that to some extent we could relax the Bondi-Meissner-Sachs boundary condition around scry, and then there is all this discussion about which actually contour terms to add to kill the divergences, if you say allow for instance, the sphere metric to fluctuate and so on and so forth. So so
Yeah,
I'm wondering about what makes the thing unique. I mean, without any.
Yeah. Okay. So basically, what I told about asymptotically flat spacetimes, it was a result from 90s. So it was only assuming BMS group, but in our case, we assume the usual initial conditions at null infinity for the sitter, so that we give arbitrarily G and T. So there is no restriction on initial data.
You assume that conformal structures.
No, we don't. I mean, we don't assume that G0 is conformally flat because it's unphysical restriction.
Okay, and then you say the thing is unique.
Yes, because basically we don't have any functionals which are conformally invariant and depends analytically on fields.
Okay, and this is the same prescription as the compare in paper, or is in the compare Fiorucci-Ruzziconi paper?
I think that in compare. I'm not sure.
Okay. Okay, thank you.
Thank you.
Okay, I have comment about this data. I could call them conformal ADM data on space like Scry, you know, just
It makes sense.
Conformal metric and transverse traceless tensor, which is a density, and this is the ADM momentum, symplectic momentum counterpart. So this ADS CFT correspondence makes some chaos within the interpretation of this. But this, from canonical point of view, is just ADM momentum. It has nothing to do with the matter and the energy momentum tensor. So
yeah, it's true.
Yeah. Okay, so we should continue. Let's us thank the speaker again. The time is over.